Okay, so in section 12.5, we learned about some applications of double integrals, in particular the moments, the center of mass about a lamina. Okay, and this comes up in engineering physics applications. And double integrals also come up in probability and statistics. We just don't have the time really to, to cover that in here. But I encourage you to take a course on that in the future. So another application of these double integrals is surface area. Okay, now are there some shapes, some surfaces that we know how to get the surface area for? Like, let's say a box. Let's say a cardboard box. Could we find the surface? Okay, a cube. Yeah, that's right, Christopher. We could find the surface area for a cube. Okay, we could find the surface area for anything else that we know formula of. A pyramid, sure, Christopher. That's right, Robin. Rectangular prisms, cylinders. Okay, so there are some nice formulas. Spheres, absolutely. There are some nice formulas where we can find surface areas of surfaces, but we want a more general way to find surface area, because not every surface is a cylinder or a sphere or a prism or a box. Okay, and so this is what section 12.6 deals with. So first of all, they remind you that in section 10.5, okay, you studied where if you had a vector function of two parameters, u and v, that vector function would actually trace out a surface in three-dimensional space based on those parametric equations. And of course, if we wanted to find the derivative with respect to variable u or variable v, we're able to do that. Okay, we're able to do that by taking partial derivatives. Okay, so the partial derivative of this vector function with respect to v would mean that you differentiate every component, the three components, I, J, K components. You differentiate the coefficient functions with respect to v. And of course, if you are going to hold on here, if you're going to find the derivative of your vector function with respect to u, you would take the derivatives of the coefficient functions for I, J, and K, holding the v constant and differentiating with respect to u. So and you've learned about this. And let's think in terms of what you already know. The u and v variables form some region D, okay, in the xy plane. Well, it's not xy plane, it's the uv plane. I mean, certainly this, every time we have a double integral, we have to identify a region D. Well, here, this region D they're drawing is in the uv plane, and of course, if you have your derivative vectors, remember what those mean. What do those derivative vectors stand for? Well, if you pick a point on the surface and you draw two contours on the surface, okay, a C1 contour and a C2 contour, the C1 contour is the tangent vector is the vector r, the derivative of the vector r with respect to v. So that means you're holding u constant, and the tangent vector r sub u is the tangent vector where you take the derivative of r and hold v constant. And naturally, those tangent vectors would be tangent to the curves, the space curves. You know, because anytime you hold one variable, if you have a vector function, you hold one of the variables constant. I'm sorry, if you have a vector function of two variables and you hold one of the variables constant, you get a space curve, and that's what you see here in Figure 1. You have two space curves along that surface, two space curves C1 and C2, and then you have these derivative vectors, tangent vectors, at the point P sub 0. Okay, so so far, are there any questions with this? All right, all right. Well, now what we want to do, of course, is we want to find the surface area, say, of a surface that looks like this. Okay, all right. And how would you do this? Well, naturally, it's sort of natural to think of, in Figure 2 here, you have on the right, you have a surface, and it's like a quilt. It's like a quilt, and the quilt has different patches on it. And if you could find or approximate the surface area of each little patch, S sub ij, in that surface on the right, you could add up the areas of all those patches and get an approximate value for the surface area. And naturally, as you look at different patches, you're going to be above different little subrectangles in the UV plane on the left. Okay, so how do we find the surface area of a patch? Well, what we can do, we can approximate it, of course, by what they're showing here in Figure 3. So in Figure 3, you have a patch. You have a patch S sub ij, and the patch, you have a point on the bottom left corner of that patch, and you're drawing two vectors to those endpoints on the patch, and basically you have a parallelogram. If you look at the two vectors in Figure 3, and then you go down to Figure B, you can see that we can approximate or B in Figure 3. You can see that we can approximate the area of the ijth patch with the area of a parallelogram. Okay, now the area of a parallelogram, of course, it's critical to know the vectors that form the sides of the parallelogram. You see, a parallelogram is more general than just a rectangle for a general patch, and that's why we use a parallelogram. The tangent vectors to the point P sub ij are the derivative vector r with respect to u and the derivative vector r with respect to v. But of course, if we want to make our patches smaller and smaller, we can multiply those derivative vectors by a scalar delta u and a scalar delta v. I mean, there's nothing wrong with that. There's nothing wrong with that. Okay, delta. So we want a small patch, because a small patch is basically going to be very well approximated by the area. The surface area of a small patch is very well approximated by the area of a parallelogram. Okay, well, now to find the area of a parallelogram, what's involved? what special operation between the two vectors is involved in helping you find the area of a parallelogram? Do you recall? Well, it's going to be the cross product. Well, Robin, you are right about the base and height. And we actually have to go back to section 9.4. So let me go back to section 9.4, because well, what they're going to say here, hold on here. What they're going to say is that the surface area, or the area of the approximating parallelogram to the ijth patch, is given by the magnitude of this cross product. The cross product of the dot of the cross. I'm sorry, it's the magnitude of the cross product of the two vectors that form the sides of the parallelogram. Okay, so but how do we get that? How do we get there? Well, let me go back here into hold on here. I want to go back. Let me see. Hold on, class. I don't want to do that. Let me stop sharing for a minute. Took me to an area I didn't want to go. All right, I'm going to go back to section 9.4. I'm going to go back to section 9.4. And I'll project it here, but you do have your ebooks. And let's see. I want to go to right after example 2. Okay, so let me project that. Okay, so you see here, I mean, I'm going to say this the right way. The cross product, the original definition of the cross product of two vectors was the magnitude of the vector A times the magnitude of the vector B times the sine of the angle between the vectors. How many recall that from back in chapter 9? I know it's been a while, but okay. Good, Ryan, good. And so, okay, that then, well, look at figure 6. In figure 6, they have a parallelogram, and they want to find the area of the parallelogram. So you see what they do, they have a cut along that triangle there on the left. If you were to move that triangle and place it on the right, it would fill in the gap. It would fill in the gap on the right side. In other words, let me phrase it another way here. Hold on. Let me phrase this another way. Maybe I'll put this in red. Hold on. Man. Okay. Okay, so there's a vector. And there's a vector. I'll call this vector A, and I'll call this vector B. Okay, and clearly we can complete the parallelogram like you see. But see what we're going to do here, and maybe I'll keep the line here. We're going to cut off this part of the parallelogram. Okay, and just get this junk off here. I mean, it isn't junk, but I want it to look good. There's my angle theta. And I think you agree that the area of the parallelogram would be found by finding the area of that triangle and the area of that shape. Well, what if I were to move this triangle over here? What if I were to move that triangle over there? Okay, if I were to move that triangle over there, okay, then the area of the parallelogram could be represented by, hold on, sorry. It could be represented by this length, okay, which is the magnitude of the vector b, because, you know, it is. And this height. And this height is just the, well, the sine of theta hold on, I'm going to try to draw, I'm going to try to write well here. The sine of theta is equal to this y, okay, that y, over the hypotenuse. Well, the hypotenuse is just the length of the vector A. And so y times, hold on here, y would equal, y would have to equal the magnitude of the vector A times the sine of theta. Well, if you take the base times the height, here's the base, here's the height, that, and then, you know, it's area, so take the absolute value. The area of the parallelogram can be represented as the area of, I'm sorry, the area of the parallelogram can be represented as the magnitude of the cross product of the AB vectors. That's what they're trying to, get across in this picture here. Okay, is that helpful? Are there any questions on that? Hold on. Okay, Robin's good. All right, good. Ryan's good. All right, well then, now that we've are intuitively we're comfortable with that, then we can continue back into section 12.6. So let me now go back into section 12.6. One moment here. Just give me a moment. Okay, now let me okay, so let me double click on that. So now here's our parallelogram in figure 3b, and we're just going to take the cross product of those two tiny vectors, delta v times the derivative of r with respect to v, and delta u times the derivative of r with respect to u. So we're going to take to find the area of the parallelogram, we're going to take the magnitude of the cross product of those two vectors. And that's what they have, that's what they show up here. Okay, did everything, let me just see here if you were able to see. Yeah, you saw the pictures okay, class? Everybody's good? Okay, good, excellent. All right, and so here is the magnitude of the cross product vector, and the delta u and delta v can be made smaller and smaller so that the area of each parallelogram more closely approximates the area of each patch on the surface. Of course, the cross product, you can factor out those scalars. That's one of the properties of cross product of two vectors. If you have a cross product of two vectors and there's multiples scalars multiplying each vector, you can just factor those out. And so an approximation then of the area of the patch can just be given by, amazingly, by this double Riemann sum. Okay, by that double Riemann sum. And what's that double Riemann sum going to turn into as we let delta u and delta v get smaller and smaller? What would that, and take the limit? Of course, if we do that, we have more patches, and that means m goes to infinity and n goes to infinity. What would this Riemann sum turn into? That's right, Ryan, a double integral. And that's what we get. So now, with the power of hold on, let me get that up a little bit. Now, with the power of multivariable calculus behind us, we have a way to find the area of a surface. Okay, we have a way to find the area of a surface. And of course, for the surface, you have to identify what your vectors are going to be, your r and your v. Yeah. Okay. Are there any questions on that? Okay, well, the book has some nice examples. The book has some nice examples here. Let's talk about the surface area of a sphere. Now, you had told me there's a formula for that, but where did that formula come from? Can we derive it using this nice double integral formula? for the area of a surface? The answer is yes. The answer is yes. So in example one, they want you to find the area of a sphere of radius A. So, of course, finding the parametric representation for the sphere is necessary. And we know that if we have x, y, and z as defined that way, you know, where you have angles theta and phi and radius A, that's a parameterization. That's a parameterization that we can use. Okay, so in other words, if we wanted to take a vector r as a function of phi and theta, and we let those angles, and they're in radian mode, we let those angles vary. Phi would go between 0 and 180 degrees, and theta would go between 0 and 360 degrees. But if we follow this, if we let x, y, and z be defined by these formulas, the vector r, which consists of these components x, y, and z, will trace out a sphere of radius r in three-dimensional space. Okay, and you let phi range from 0 to pi, you let theta vary from 0 to 2 pi. So, you know, to use this formula that we just learned, we need to know the vector function r. We need to know its parameterization. Well, now that we know, well, are there any questions so far before we move forward? Okay, well, let's keep moving forward then with this. So, okay, so here is the cross product. Okay, the cross product between these two vectors, these two derivative vectors, one with respect to phi, one with respect to theta. And we get that cross product below. So it's just a matter of using, you know, of computing a cross product. And now we want to find, you know, based on the formula, we want to find the magnitude of this cross product vector. Okay, we want to find, because the formula, in the formula here, we have to find, before we can integrate, you know, we need a function to integrate, right? Well, that's going to be the magnitude of the cross product vector. Now, they have u and v as their parameters, but for example one, we're just using phi and theta. All right, so we move forward here. All right, so of course, you compute the magnitude of a vector the way you would any vector. The cross product of two vectors is a vector. You just square each of the components and add them, and then of course square root of all of that. And with a little bit of factoring here, it turns out, let me just see, they're factoring out, let me see, look at what they're doing here. Well, the first two terms, because sine squared plus cosine squared equals 1, the first two terms are going to be equal to a to the fourth times sine of fourth of phi times 1. And that's how you get the a to the fourth times sine to the fourth of phi. And then the third term there is just there under the square root. But what you can do now is you can factor out a sine squared of phi from both terms, and then you're going to be left with under the square root here, you'll be left with the square root of a squared times the sine squared of phi times hold on here. No, you're going to factor out a to the fourth times the sine squared of phi. If you do that, you'll have a to the fourth times the sine squared of phi times the sum of sine squared of phi plus cosine squared of phi. That just equals the 1 by the Pythagorean theorem, or Pythagorean identity, I should say. And so you end up with the square root of a to the fourth is a squared. So you're going to end up with, turns out, a squared times the sine of phi. And that's going to be then, that's what you're going to end up with, right? So is everybody okay with how they did this? So the first two terms, they factor out an a to the fourth times the sine of fourth of phi, and they're left that factor is multiplied by the sum of a cosine squared and sine squared of theta. Well, that's just equals to 1. So you get a to the fourth sine fourth of phi, and then what they do is from the square root there on the bottom, they factor out an a to the fourth sine fourth of phi, or a to the fourth sine squared of phi. And then they're going to multiply a to the fourth sine squared of phi by sine squared of phi plus cosine squared of phi. That equals 1. And you're left with the square root of a to the fourth times sine squared of phi. That becomes a squared sine phi. All right. And so now we're ready to compute our double integral. Of course, we know the limits for our parameters. And in this case, we can actually write that double integral as the product of two integrals. And it turns out that we're going to get 4 times pi times a squared. So the surface area of a sphere with radius r is 4 times pi times, the surface area of a sphere with radius a is 4 times pi times a squared. Okay, so see, you use calculus. How many of you have never seen a proof of that formula? Maybe this is the first time you've seen that formula proven. Okay, first time for Christopher, first time for Robin and John and Ryan. Yeah. Well, you see, that's the beauty when you take higher level courses, you can prove things. So this is fine. So we have a very general formula here. This surface area formula is a very general formula. But what happens is, of course, if your surface can be treated as a function of x and y, then this surface area formula can take another form, which students kind of like. I personally like to use this formula all the time, but let me just show you here. So let's say that, hold on here. Let's say they talk about, hold on. I want to highlight that actually. Am I able to do that here? Yeah. So if you have z as a function of x and y, then the parametric equations for the surface, you can let x be x, y be y, and z equal a function of x and y, right? And so if you take the partial derivative of r, okay, with respect to x, okay, as they show here, you would get that vector function r, the derivative of r with respect to x. And similarly, you can take the derivative of r with respect to y. But do you see how you would, are you okay with how we got this? This is for the special case when z is a function of x and y. Are there any questions on that? The second component, the j component, well, actually, there's two vector formulas here. They just forgot to put a comma between them. The derivative of r with respect to x, okay, you hold the y constant. That's just going to give you I plus the partial derivative of f with respect to x times the k vector. And then the derivative vector with respect to y would just be j plus the partial derivative of f with respect to y times the k vector. Okay, so in one case, the one component drops out for each of the vectors because you're holding one of the variables constant, right? And you got that parameterization. Well, so now what you can do is you can consider, well, let me take the cross product. Let me take the cross product of those two vectors, and if you do, you're going to get the cross product of those two derivative vectors is going to equal negative the partial derivative of f with respect to x times I minus the partial derivative of f with respect to y times j plus k. And so now given that, you have another formula for the area of a surface. But it's only true when z is a function of x and y. Okay, are there any questions on that? Okay, well then let's look at a second example here. Let's keep going. So here they want you to find the surface area of the part of the paraboloid that lies under the plane. Okay, so all right, does this paraboloid here in example 2, does it go up or down? It goes down. Wait, no, it goes up. Has to go up. You're used to paraboloids that go down, but this one goes up. But it doesn't go up forever. It's cut off by the plane z equals 9. So given that, if we look at the picture of the paraboloid, okay, there's the picture, and we want to find the surface area of that surface. Okay, we want to find the surface area of this blue surface that you see. Okay. Okay, so, well, all right. The region D is a circle. Okay, if we compress that solid down into the xy plane, we get a circle. We get a circle here. So when you have a circular region, do you think it's better to use Cartesian coordinates or polar coordinates for integration? What do you think? Yeah, let's try polar coordinates. I agree with Christopher. Let's try polar coordinates. Okay, well, all right. So what they do is they, of course, first, z is equal to, z is equal to, hold on here, one moment, class, one moment. Yeah, the paraboloid, the surface, z equals x squared plus y squared. So we compute the partial derivatives of z, which are 2x and 2y, and we end up with this. And you notice that double integral, they've not committed yet to what the region D is or what they're going to integrate with using Cartesian or polar coordinates. But based on the picture below, we're going to use polar coordinates. And so now for, hold on here, one moment, class. Now for square root for x squared plus y squared, they put in an r squared, and you get this integral. You're able to separate the integral into a product, and the second integral, you can do a u substitution, let u equal 1 plus 4r squared, and you go through the details, and you'll get the answer they get. Okay, so you see the book, to save space, they leave out steps, but of course, you know, for your exam 3, I'm going to want to see those steps. Okay, I can't give credit even if you get the right answer unless I see your work, and the work has to be good work, right? Because I'm testing your understanding of calculus 3 concepts. You know, I don't want you to be an engineer someday and not know calculus 3, right? Okay, are there any questions on this? Okay, all right. Let me stop the recording then.